All right, so let's go ahead and begin. First of all, there's quite a few handouts on the table. Um, there's the CPU diagram or the CPE233 microprocessor diagram that I put on the table a few times previously. So that's on the table, just one copy. But then there's two other handouts that I made enough copies so each person can have one. One of them is my midterm policy and also the topics for the midterm, because as listed on Canvas and in the syllabus, so this isn't a change. This is just a reminder that the midterm is 2 weeks from today, so that's May 11th. So take a look at what's on that handout as far as the policy and the topics, and then next week if you have questions, you can ask questions then. So I'm just giving you a heads up about the midterm. It's 2 weeks away, but 2 weeks goes pretty fast. So you want to make sure you start preparing early. And then the other handout is a handout out of the Basis 3 board reference manual. I don't know if you noticed, but the reference manual, I'm pretty sure I put a link on Canvas to the reference manual. It's like a 20-page manual, and that's just one page out of the manual. And it talks about the 7-segment display that's on the Basis board. So we're going to be covering that because Lab 3, you will be using a 7-segment display. Okay, so we'll talk about how the 7-segment display works today. Okay, but as you can see from the agenda, the big topic is decoders, because again, decoder is part of Lab 3. But before we talk about decoders, there's this other format of bits called BCD, which is an acronym for binary coded decimal, that I just wanted to go over because Lab 3 as written has BCD as the input to the decoder, but we're going to change that. Okay, and I'll explain why we're doing that coming up. But I do want to go over what BCD is because it is something that comes up quite a bit. And before we talk about BCD, I just want to go over something that we've already talked about, because once students see BCD, sometimes they get confused. Okay, so I'm trying to hopefully eliminate that confusion. Okay, by first looking at something we've already talked about. Right? We talked about how to go from hex to binary, a binary to hex fairly easily, right, without going through base 10. Right? Do you remember what we do? How do we go directly between those two bases without going through base 10? Like if we wanted to take 1, 4, 5, 9 in hex and go to binary without going through base 10, how would we do it? What about the bits? Group the bits in what number? 2 to the what is 16? 4. Right. We just write each hexadecimal character as a 4-bit binary group. So what's 9 in binary? In 4-bit binary? So that would be 1, 0, 0, 1. What's 5?
0, 1, 0, 1.
0, 1, 0, 1. What's 4?
0, 1, 0.
And then what's 1? Yeah, you don't have to write the 3 leading zeros, right? Okay, so that would be our conversion from base 16 to base 2. So again, the 9 gave us the 1, 0, 0, 1. The 5 gave us the 0, 1, 0, 1. The 4 gave us 0, 1, 0, 0. And the 1 gave us 0, 0, 0, 0, 0, 1. But typically you don't write the leading zeros. Okay. So remember, this is actually converting between bases. And again, the reason why it's groups of 4 is because of the relationship between 2 and 16, right? That if you raise 2 to the 4th power, you get 16. So that's why it's 4 groupings. So, I don't think we did this in class, but hopefully on your own, you've proved this to yourself that, once you do this conversion with this grouping of 4, if you now take this base 16 number and convert it to base 10, and now take this base 2 number, right, convert it to base 10, you'll see it's the same number, right? It's the same value. Okay, so any questions on this? Again, this we've covered, right? This is just review. Okay, but here's the reason I'm bringing it up before BCD, because BCD, binary coded decimal, it's a subset of binary. Okay. See, in BCD, you have 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 0, 0, 1, 0, 1. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. See, BCD has the 4-bit binary for all your decimal numbers, characters, 0 through 9. Okay? So if I have a base 2 number, like 1, 4, 5, 9, right? This is a base 10 number, and I want to show that base 10 number in BCD, I'm doing the same sort of thing as we do when we go from hex to binary, but the key difference is I'm not doing a conversion here. This is not converting bases, okay? This is just representing each decimal character as a 4-bit binary group that we call BCD. So even though it's going to look the same, right? Because, my 9 is 1, 0, 0, 1. My 5 is 0, 1, 0, 1. 4 is 0, 1, 0, 0. Now, here's the difference is in BCD, you would actually keep the leading zeros. Okay, you would write it like that. So you see this is BCD for this decimal number, but it's not a base conversion. Okay, that's the key thing. The reason, you'll see the reason coming up for BCD is because of something called a 7-segment display. Okay. Right. So any questions about BCD? The key thing to remember is that we're not doing base conversion.
Basically, not converting binary, but you're later in binary.
Well, you'll see the reason why we would want to do. See, the reason we would want to do this is because of something called a 7-segment display that we're going to talk about. So, yeah, it's kind of like a to be continued. Okay. Once we see what a 7-segment display is, I'll kind of come back and say, okay, this is the reason for BCD. Okay, but the key point I'm going to make at this point is just that we're not doing a base conversion. So even though it looks the same, this is actually converting bases. This is not converting bases because this BCD would not equal this base 10 number. It would equal that number in base 16.
You're just gonna like build out. Oh, okay, that happened. If I was wondering if there's like a notation that denotes that it's in BCD.
Yeah, yeah, you would put a subscript BCD. Yeah. Yeah, otherwise you don't end up getting so. Okay, so the next thing is to talk about decoders. Okay, and the definition of decoders is very broad, and that's because just about anything in the digital world could be called a decoder. Okay, because the definition of a decoder is that it's a device that converts digital signals. Digital signals are just bits, right? Digital signals from one form to another. Okay, so there are many logical circuits that you could call a decoder. One example, there are many, but one example in CPE133. Okay, the follow-on to this class, and this is the reason why I have diagram of the microprocessor that you build in CPE133 on the table is that if you look at this diagram and you look up towards the upper right-hand corner, you'll see this box component that's labeled CUDCDR, and that stands for Control Unit Decoder. So you see in CPE133, have this control unit, that's what CU stands for, DCDR decoder. And what this decoder is doing is that it's taking an instruction. It's a 32-bit instruction, and it's converting it into, so it takes the instruction and converts into mux select bits, right? Because if you look at this this box here for the control unit decoder, coming into it, you'll see this IR and then 14:12. What that is that's 3 bits. It's 14, 13, and 12 of an instruction. And then it also has IR30. That's the 30th bit of an instruction. And then if you look up where there's a /7, for 7 bits, it goes up to another IR6 to 0. That's another 7 bits of an instruction. Okay, you'll learn in that class that the instructions for this microprocessor are 32-bit long. And the decoder is taking certain bits. And from those certain bits, it's converting it into outputs. Now, if you look at the right side, you got output ALU fun, ALU source A, ALU source B, PC source, RF, WR, SEL. So you see there's these 5 outputs. And then if you look in other parts of the diagram, you'll see that those 5 outputs of that control unit decoder, they go to the select inputs of mux. The ALU fun goes to the ALU, which when you take that class, you'll learn that that ALU is basically a big mux. It's a big mux that can do mathematical logical operations. And then ALU source B is the select to the mux that's at one of the inputs of the ALU. The ALU source A is the select input to the mux that that connects to the other input of the ALU. The PC source is the select input to this mux over by the program counter. That's what PC stands for. And then RFWR select is a select input that goes to a mux that's by this thing called a reg file. Okay, so you see that decoder in CPE133, it's converting an instruction, which is a digital signal because it's made out of bits, and it's converting it into outputs, which are either 0 or 1. So again, into another digital signal, and by outputting these mux select bits, what's occurring is that the control unit is routing the data through the microprocessor. Okay, so it's taking instructions, and then through the use of those outputs, which are connected to the select inputs of the muxes, it's how the data gets routed through the microprocessor. Okay, so that's an example of a decoder, right? It's taking one form of digital signal and instruction and turning it into another form, which are outputs that go to select lines that have the purpose of guiding data through the microprocessor circuitry. Okay. Well, did I pick yours? Oh no, this is mine. Well, in this class, okay, so in this class, you're going to build a 7-segment decoder. See, it's going to take the digital signal that's coming from your RCA, right? That represents some number. And it's going to convert that into seeing that number as a hex character on a 7-segment display. Okay. And it's a part of lab 3. Okay, it's here's our lab 3 diagram. We talked a little bit about this last week, right? You got the RCA, which you designed last lab. Also, there's this MUX that, well, how many people were able to get a successful simulation of the MUX last time? Okay, not too bad. Probably about half the class. That's okay. Well, you have this other piece here that's the decoder. See, this is the 7-seg decoder. Now, in the lab instructions and in the diagram that's on Canvas, by this input that connects to the sum output of the RCA, it has BCD, the binary coded decimal. But I'm going to have you change it to hex. Okay? And I'll explain exactly what all that means coming up. But I just wanted to note here, just so you don't miss this, that we're changing this from BCD to hex, and I'll explain the reason why we're doing that, and what effects it has on the design you're doing. Okay, but before we move on and talk about how these 7-segment displays work that are on your Basis 3 board, again, just a little bit of a review here. Remember, you've seen this before because you saw this with the RCA, right? That I had this dash box, right? And with the RCA, the half adders and the full adders were inside the dash box. And then outside the dash box, we have our main inputs and our main outputs. So where are our main, what diagram do we show our main inputs and our main outputs? Right, the high level black box diagram, right? So you see for your lab 3, high level black box diagram, what inputs are you going to have? Yeah, it's A and B, right? Let's see how I got them outside the dash line. So those are your high level. So you see you're going to have your A and B coming in, right? And they're both 4 bits. Okay, and then what are your main outputs? So what outputs are we going to have in this high level black box diagram? Which segment? Yeah, right over here. Now we're going to go over what these are, but when you're coming up with your high level black box diagram, this is what you're doing. You're just seeing what's feeding into my structural model. Okay, remember the structural model, that's what this is made out of, right? That's why we call this high level, because it's not that detailed, right? That's why we call a structural diagram a low level, because it's more detailed. That's what we mean by low level. Okay, so yeah, you're going to have 2 outputs. This is a 7-bit output, seg, and this is a 4-bit output, an. All right, so that's what your high-level black box diagram looks like for lab 3. Okay. Now we'll come back to this and we'll go over exactly what's going on here. But before we do, we got to talk about the 7-segment display and how it functions. Okay. And you've all seen the 7-segment displays on your Basis board, right? There's 4 of them. Okay, and all 4 operate the same way. Okay, so the first thing about a 7-segment display is that it has 7 segments, as you would think, right? And those 7 segments are oriented like a figure 8. And there's basically 8 pins. Okay, 1 pin is AN. For those of you that know, well, how many people know what a diode is? You people know what a diode is? Okay. Well, if you know what a diode is, and again, for this class, you don't have to know what a diode is, so don't worry if you don't know. But if you know what a diode is, you probably know what AN is short for. Because what part of a diode starts with AN? Anode. Anode, yeah. So this is just short for anode. See, this type of 7-segment display is called a common anode. Common anode. Okay. Okay, then you have these other pins over here that are labeled, as you can see, with letters A through G. And by convention, okay, and this is something that's actually I've never seen it different. You know, there's a lot of things in engineering where, you know, things aren't standard, you know. But as far as I know, all 7 segment displays, the segments are identified this way. The top segment is the A segment. This is the B segment. This is the C. The bottom is the D. This is E. This is F. And then the middle segment is G. Okay. Now, what I have drawn here, this is how a 7-segment display is constructed. Okay, the segments inside. Each segment is an LED, an individual LED. So you have 7 LEDs. And the way that the basis for 7-segment displays are that between this AN and where the segments are, where the LEDs are, there's this inverter. Okay. Now, again, if you know what a diode is, and an LED is just a diode that under the right conditions will give off light. So when you look at a diode symbol, the arrow with the line here represents an LED, which again, is just a diode that gives off light. This side, okay, the arrow side, that's called the anode. Okay, and then the other side of the LED, okay, where the line is, that's called the cathode. Okay, well, to get an LED to light, you need to have a voltage difference across it. And remember, we talked about how 1s and 0s are just voltage levels, right? Ideally, a 1 is some plus amount of voltage. Usually it's 5 volts, sometimes it's 3.3 volts. A 0 is 0 volts. Okay, we call 0 volts ground. Okay, and you'll learn this in circuits. Okay. Well, to get an LED to light, you would need a 1 on the anode side, and you would need a 0 on the cathode side, because that would give you the right voltage difference. Okay. Now, because of this inverter, in order to get a 1, okay, where the anodes are, because you see this line here is connecting all the anodes together. See, that's why it's called a common anode, because all the anodes of the segments are all connected to the same, what we call a node or connection point. And as I mentioned earlier in the class, when we connected inputs of gates together, and we said, well, when you physically connect inputs of gates together, that makes the same value for those inputs because it makes it the same voltage. Well, you see, same thing here. When I connect all these anodes together, they all have the same voltage, right? So if I have a 1 on this side of the inverter, all the anodes of all the segments are going to have a 1. Well, because there's this inverter here, in order to get a 1 to this common anode point, I would have to make AN a 0. Okay. Now, let's look at the other side of the LED, okay, the cathode side. Well, as I said a moment ago, in order to get an LED to light, you got to have a voltage difference. And again, we only have digital signals, so we only have 2 choices. Right? Either have 1, some plus amount of voltage, or we have 0, 0 volts. So in order to get a segment to light, I would need to put a 0 on the cathode of that LED. Okay. So if I put a 0 on the cathode of segment A, and there's a 1 on the anode, well, then that segment will light. Okay, because I got a voltage difference. But if I put a 1 on the cathode of one of the segments, it won't light, because if I have a 1 on both sides, that's not a voltage difference. The voltage is the same on both sides. And as you'll learn in circuits, in order for current to flow, you need a voltage difference. If you have the same voltage on both sides of some element or device, no current's going to flow. And if no current flows, it's not going to light. It's the current that flows through the LED that gets it to light. Okay? So, what this boils down to is that this AN bit controls whether whether the display will light at all. Okay, because if I make that common anode, if I make that 0, right, by making the input to this inverter 1, the LEDs cannot possibly light. And you may say, well, wait a minute, Gary, why is that so? Because if I have a 0 on this side and I put a 1 on this side, isn't that a voltage difference in what it light? Well, it is a voltage difference, but the LED wouldn't light because LEDs only allow current to flow one way. They only allow current to flow with the arrow. And in order for the current to flow with the arrow, the anode has to be a higher voltage than the cathode. So if you have an LED and the cathode is a 1 and the anode is a 0, it won't light, even though it has a voltage difference. And that just goes to how a diode is fabricated. And again, you're going to learn all the details of that, later on. Okay. So this AN, it controls whether the display will light at all. These segment cathodes, okay, all these here, these control which segments light. So you see, if I want to turn a display off, I can use this. To get whatever LEDs I want to light, so I can make whatever character I like. Say I want to make base 10 characters, 0 through 9. I can do it with this 7-segment display by just lighting up the appropriate segments. If I want to light up hexadecimal characters, right, 0 through 9, then A, B, C, D, E, F, I can do it with some modification that we'll get to by just lighting the appropriate segments. Okay, and you see that's what this decoder does. This decoder takes the binary that's coming from the RCA and converts it into the cathode bits that we need to get whatever character we want. So we can have this be a BCD decoder, right? That takes this binary and shows decimal characters 0 through 9, or we can make it a hex, right? Which shows 0 through 9, then A through F. So you see, the only difference that you're going to see in a moment here between having this BCD and this hex is that with hex we'll have a bigger truth table, right? Because you got more characters in base 16 than you do in base 10. Okay? So that's why I'm changing this from BCD to hex, because it's a little bit more interesting. Okay. And you see the reason why BCD is so popular is because lots of times you want to display decimal numbers on 7-segment displays. So that's really the reason for BCD. It's just showing the binary you would need into a decoder to get whatever decimal character you want. And again, that's why it's not a conversion. It's just something to do with 7-segment displays. All right, so did that make sense? Now, I realize again, I had to talk some circuits, a little bit of circuits. Don't worry if you don't understand all the details of the circuits, you're not going to get tested on that. The key thing is sort of in a summary, the key thing is this bit controls whether the display will light at all. Okay, and then these bits control which segments are going to light. And like I said, on the basis board, you have 4 7-segment displays. They're all the same. So that's why, see this AN output? See how it has 4 bits? The reason why it has 4 bits is because 1 bit is going to display 0. So that would be A0. AN1's going to another display that we call display 1. AN2 is going to display 2. AN3 is going to display 3, because there's 4 7-segment displays. And they all have 7 segments, so each one has an A, B, C, all the way through G segment. All right, so, I didn't feel like repeating this 3 more times, but I guess to be complete, to really show what's on the basis board, I'd have to write this out 3 more times, because there's 4 of them. But, you understand how one works, the others work the same way. Okay, let me turn the camera before I forget. Okay, but any questions before we go to the truth table? Now, like I said, one of the handouts is a reference page out of the basis 3 board, and it talks a little bit about what I went over. Okay, so you can use that as a reference. All right, but the next thing we're gonna do here is we're gonna come up with our truth table for a hex to 7 segment decoder. You're gonna need this for when you model that decoder in System Verilog. Okay, so the first column here, I'm gonna write the hex character along with the binary. Okay, so you have your 0 hex character, and of course that's all zeros. And I'm writing it as 4 bits because that's what's coming into our decoder from our RCA. So if we have a 0 coming into that decoder, what we want to see on the 7-segment display is we want to see all the segments light except for the middle segments, right? So we want to see this. Oops, you don't want the middle segment. Stay there. Right, so you see when we have a 0, we want all the segments to light except for the middle one, right? Because that would show us a 0. So now, these are what our seg bits are going to be. See, this is our seg. Right, this is our 7-bit seg output because we have 7 cathodes. Right, you can see I have G through A here. So if I want a 0 to show up on that 7-segment display, what cathodes do I want to be 0 and what do I want to be a 1? A through F. A through F should be zeros. Yeah. Right, yeah, because remember, it takes a 0 to light a segment. So yeah, all these segments would have to be 0. So only the G segment would be a 1, right? So you see, you just write 1 0 0 0 0 0 0. Now, as we talked about, we can go from hex to binary or binary to hex just by grouping bits in 4s, right? So what if I wanted to write this seg output as a hex instead of a binary? How would you write 1 0 0 0 0 0 0 as hex? 0 4 4 0. How many people say 4 0? Not that many. Any other answers? How many people don't know? Yeah? A lot of honest people. Okay. It's the same as what we did here, but going the other direction. Right, see here we went from hex to binary by writing each hex character as a 4-bit binary group, but you can go the other way, right? Take 4-bit binary groups. You always start with the least significant bit and write the 4-bit binary group as a hex character. So you see, I would start here. Okay, so that's going to give me 0. And now you would just put like an imaginary 0 here. Right, so 0 1 0 0, that's 4, and 0 0 0 0 is just 0. So you see, this would be 4 0 hex. See again, the convenience of hex in the digital world is just I don't have to say as much, right? Instead of saying that the seg output is 1 0 0 0 0 0 0, I can just say it's 40 hex. Right? See, that's the convenience of basic key when it comes to digital. Do you have a question? Oh.
Can you explain again why this is the 1?
Yeah, it goes back to what we talked about over here, that see, each segment is an LED, and in order to get the LED to light, the common anode has to be a 1, and the segment has to be a 0. If you have a 1 on both sides of an LED, it won't light. So because, a 0 is all the segments lit except the middle one, I only want the middle one to be a 1 because that will shut that off. Yeah. Okay. So the activity today is to complete this table. Now, was one enough, or do you want me to do another example? Does anyone want me to do another example? Okay, which one do you want me to do? Because how many rows are we gonna have in this truth table since it's hex? 16, right? Because we have 16 characters in that. So just tell me which row, which one, what hex character do you want to do? 13. 13. All right, so let's see. 1, 2, 3, 4, 5. 13. Oh, well, actually, do you want it to be number 13 or do you want it to be row 13? Which one?
Either is fine. Number 13.
Number 13. Okay, so let's see. It'd be so be here. So 13. Oh, and what's 13 in hex? What character? D. How many people say D? How many people don't know? Well, what the people that do know but don't think it's D, what do you think it is? What's the other? You see, what I always do, because you always have to think about it, right? We don't deal with it every day. What I always do is I know A is 10. So I'll just go from there, right? If A is 10, B is 11, C is 12, so D would be 13. I guess you could start with F, 15, work your way backwards, you might get to the answer sooner, but I always start with A equals 10. Okay, I elapsed my row now. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, so B here, right? Yeah. All right, so D, and what's D in binary? So what's 13 in binary? 1101, right? You guys remember, that's what's coming into our BCD or our hex seg decoder, right? It's the binary coming from the RCA. Okay, so actually, I'm glad we picked this one because this comes up with one of the modifications we're going to have to make. You know, as I said in an earlier class, it's not completely standard, but most of the time, once you get to the letters in base 16, most of the time people use uppercase. It's not something strict. In fact, when you take CPE133, there's professors that teach that class and you know, they don't care about the case. But here we do have to make a modification because what's going to happen when I try to make a capital D? It's going to look just like a 0, right? And that's because of the limitation of this display. It only has 7 segments. You know, there's other type of displays that have more segments. You know, you can get a display that has like 16 segments and they have some at angles, you know, so you can make like W's and things like that. But, you know, we're restricted because there's only 7 segments. So because a capital D would look like a 0, we'll use lowercase d. So instead of a capital D, you know, we'll use lowercase d. So let's see, we're going to want to light up these segments, right? Make a lowercase d. Okay, so to make a lowercase d, is this in the way? So what segments do we want to light, or which segments don't we want to light, right? It's probably easier to say the segments we don't want to light because there's fewer of them. A and F. Right, yeah, we don't want A and F, right? If A and F are off and we like the others, that would be a lowercase d. Okay, so what does that tell us about these bits here? What's going to be, what's that?
Yeah.
Yeah, A and F we don't want lit, so we have to make those cathode bits equal to 1, right? Because remember, a 1 will not like the LED, right? Because that puts equal voltage on both sides. So let's see. So the G is going to be a 0 because we want that lit, but the F is going to be a 1. E is going to be a 0. D is gonna be a 0, C is gonna be a 0, B is gonna be 0, and A is gonna be a 1, right? So did I get that right? I didn't mess up A, B, C, D, E, F, G, right? Okay. So does everybody agree 0, 1, 0, 0, 0, 0, 1, that would give us the lowercase d? Okay, so now what's that in hex? 21, yep, right, because these 4 bits give us 1. These 4, again, imaginary 0 there, give us 2, so this would be 21 hex. Are you starting to see why we use hex, right? Because isn't it easier just to say 21 as opposed to 0, 1, 0, 0, 0, 0, 1? And in CPE133, you're going to have 32-bit pieces of data. So do you want to say 32 zeros and ones, or you rather just say 8 hex characters, right? Again, that's the whole reason why we convert binary to hex. So do you think you could do the rest? Oh, what's the other character that we're going to have to modify when we get to letters? Right. You don't want to use capital B, right? Because what's a capital B going to look like? An 8. So you're going to have to use lowercase b. Okay, but do you think you can handle doing this table now?
For one, do you want F and E or C and C?
Oh, it'd be B and C.
Oh.
Yeah, because on the display, like, because just think, like your 3 is going to be like this, right?
Yeah.
And on your display, like if these 2 lit, it wouldn't look
Right.
yeah. So yeah, you want to. I understand your question, but yeah, it'd be B and C.
Okay, yeah, thank you.
Sure. Okay, so the activity today is going to be just completing this table. You know, each person do their own table, then again, just pass one in for your table. All right, the next thing is to talk about how you're going to model the 7-seg decoder in System Verilog. And we're going to have you use, instead of, because you could do this. You could come up with a truth table for all these outputs. Like you could do well, when I say truth table, also K-map, right? If you wanted to get the reduced expression for all of these segment outputs, you could do it. You could have like a K-map for G, a K-map for F. They would each be 16-cell K-maps, right? Because each output has 16 inputs, right? I mean, you could do that, you know, and then write out the Boolean expressions. Okay, like you did, you know, in the previous labs, right? But again, this is where instead we're going to use the power of the software of Verilog. Last class, for the MUX, you saw how to use an if statement. Okay, and what did that if statement have to go within? Like we put an if statement within what? And always comb. Right. What does the comb, the C-O-M-B stand for? Right, combinational. What do we mean by combinational? Combinational logic. It doesn't have what? Memory. Right, exactly. And if you don't have memory, you also don't have this thing called a clock. Okay, in a couple weeks, in fact, I think the week after next, okay, the same week as the midterm, but I think before the midterm, we're going to start talking about sequential circuits. Sequential circuits do have memory, okay, and they do require a clock. So they're sort of like the opposite of combinational. Okay, but decoders are combinational. There's no memory, no clock. So just like an if statement goes within an always comb, this other type of statement you're going to use for the decoder called the case statement, it also has to go within an always comb. Okay. Now, just like any module, you start off with the name. So maybe you call this 7seg. Then you got to declare your inputs and outputs. Now, just like when you did the if statement, and this was something that, remember, I forgot to mention during the lecture part, but then somebody caught it. I think this table over here caught the thing I omitted. And I gave everybody that you had to include here when you declare your outputs, you have to include something when you have an output within an always comb block. Remember what that was that you have to add? Your tables you remember, because you guys started.
Logic.
Right, logic. So it's the same thing here. When you know, anytime you have an always comb block, doesn't matter whether it's an if statement, case statement, or whatever it is. Any output within that always comb has to have logic after output. So, you know, for your seg output, let's say, you know, you're gonna have output, logic, and then your seg output is 7 bits, right? So you have like 6 to 0, and then seg. And you'd have to do the same sort of thing for AN, okay, the anode output. Okay. All right, so then the next thing, you're gonna have your always underscore tone, and you need the begin for it.
Yeah. What would happen if you don't use our phone for this much? On the output?
Oh, so you're saying if you didn't have an always home, but instead of just going output this, you put logic? Is that what you're saying?
Or working still did that without our phone.
Okay, so yeah, you don't have this, okay, you put this anyway. I don't know if I've ever tried that. I mean, it's necessary when you have it. If you put it when it's not necessary, I don't know if it will give you an error or just a warning, or whether it will just ignore it. I don't know. I don't think I've ever tried it. You could try it, see what happens. Yeah, but you won't, you need it when you have it. When you don't have it, I don't know if it's optional or not. Like it might not like it. I don't know. Yeah, I'm not sure. Okay, but you have your always home, then your begin, and then you start your case. Okay, and right after case, in parentheses, you put what we call the sensitivity list. And what's meant by the sensitivity list is the input that when it changes, you want this case statement to be evaluated. So for the 7-segment decoder, when this input hex changes, that's when we want the case statement to be evaluated. Okay, so whatever you call that hex input to the decoder, that's what you would put here. Okay, now this begin is for the always home, and okay, so the case itself doesn't. I'm looking at my notes here because I always get the syntax wrong. It's a good thing I look, because a case statement doesn't have its own begin, like an if statement can have sometimes. We have like multiple outputs like we showed last time. So with the case statement, the next thing that comes is just your options. So, you know, we'll have options 0 through 15, right? Because we have 16 possibilities with hex. So you can just start with 0. And as far as I know, you can just have these as decimal. You don't have to put them as binary. Okay, so this is option 0 when the input is 0. And then we just put, then it's colon. And then let's say, well, we called our segment output seg. So then we would just put our output seg and then set it equal to the bit values, okay, the cathode bit values. So for 0, we want what you see here, this 40 hex. So you would write 7, right, because there's 7 bits, tick mark, B for binary, and then you would just put those bits. So it'd be 1, 0, 0, 0, 0, 0, 0. Is that 7? 7, and then I think you gotta end it with a semicolon. And then you would do, you know, like 1, right? Seg 7, tick mark B, and then you'd have to put the 7 bits in order to light up a 1. Okay, and then you would just keep going. You know, eventually you'll get the 15. Right, so again, you'd have seg equals 7, tick mark B, and you'd have to put the bits that you need in order to light up. Well, what do you want to light up when you have a 15? What's 15 in hex? Yeah, so capital F. Yeah, there's a question over here.
What is this tag stand for? Is that what you're saying?
Well, that's just whatever you call the output. So, hex is our input, right? That's what's coming into the decoder. And we want to output the bits to light up whatever hex character those bits represent coming in. So you're essentially taking this table, right? You're taking, like this is your input side, right? This is your output side. Okay, so the case statement's just gonna have, 16 possibilities, right? Because you got 16 possible inputs. So there's 16 different outputs, right? To light up the appropriate segments to get the 16 hex characters. Oh, question. Say it again, please.
Does it go on the testing or the design?
This is the design source. Yeah, you bring up a good point that, just like you had to simulate your mux and, some of you did that last time, but if you haven't simulated the mux yet, you probably want to start with that. You had to simulate the RCA last lab. Well, after you're done with this design source, you need to simulate this decoder. So you're going to have a test bench for your decoder. And how many test cases is the decoder test bench going to have? How many rows in the truth table do we have? 16. So you're going to have 16 test cases for your decoder. And then once you have simulated this, again, I assume you've already simulated that for last week, then you got to test the whole thing. Right? Because once you have these low-level blocks done, now you're going to need a structural design, right? Just like you had that structural design that connected up the adders into a ripple carry adder. Once you're done with these blocks, now you need another design source, a structural design that makes the connections between these. Okay? All right. But there's one other thing with the case statement, that's after you have your options, you have to end it with a default option. Let's see, it's default and then semicolon. Okay, the default is if something strange were to happen and it doesn't choose any of these options here, the default will prevent your design from getting into like, an infinite loop. And you can make the default anything you want. You can decide or assign seg whatever 7 bits you want. Now, I would advise to make it something different than one of these options, but you can make it any character. Some people just make it like a middle dash, like they'll only light up G, but you can do whatever you want for the default, but you have to have a default, because if you don't have a default, I'll put a comment here, if no default, it will create, if you don't have a default, it will create a latch. Okay, like I mentioned last class, when you do an if statement, if you leave out an else, it creates a latch. In fact, you're going to see that's one way we create memory in System Verilog is by having an if statement and else. Okay, so when you want to make a memory element, that's what you do. But since this is combinational, we don't want to latch because we don't want memory. Okay, so it's the same sort of thing with the case statement. You leave out the default, it creates a latch. And then you got to end the case. So let's see, we got to end the always column and you have to end the case. The way you end the case is you just type end case, all one word. So that would end the case, and then you end the always column, and then you would end the module. End module. Good. So again, I have notes here, but I can't guarantee all the syntax is correct. I mean, I didn't try to make any errors, but you know, if you follow this and you get a syntax error, don't be surprised. It might be something I missed. Okay. All right. So, any questions up to this point? There's just a few more things I want to go over. I want to talk about the test cases. Also, I want to talk about how that circuit works. And also, I need to tell you how to do the constraints for the 7-segment display. In fact, I have an example of it that I'll probably post after I talk about it. But before I talk about those three things, are there any questions? Okay, it shouldn't be much longer. Like
There's a one, you might want to do the 7-second display, is it on the right side or the left side?
when you write one, oh, when we display a one,
Is it a B or A or?
yeah, I think you asked that question, but yeah, it's BC. You want BC, only because, you know, like when you do a 3, it's gonna be like referenced over here. So, you know, if the one's over there, it kind of looks funny. So, I mean, I understand the question, but yeah, I think most people would do BC. So, just because it kind of lines up with the other numbers. Okay, so let's see, we got 3 more things. Probably the next thing to talk about is how this circuit is working. Okay. All right, well, you all know how the RCA works, right? RCA is just adding these 2 4-bit binary numbers. When will the carry out equal a 1? When we're adding what? Or what would the result have to be of our addition for carry out to equal a 1?
And then greater than 16.
Right, it's gonna be, because once that carry out lights, that means your result's more than 16, right? If your result's less than if your result is less than 16, right, 0 through 15, you'll just have a sum, you know, from 0 to 15, and your carry out will be 0. But once your addition is more than 15, right, your carry out is going to be a 1. Okay, so everybody, that's good. Okay. Well, notice where the carry out is connected. The carry out is connected to the select of this mux. So when the carry out is a 0, what's going to happen with this mux? What do we know about muxes? How do muxes work? If the select input is a 0, what's going to happen? The output's going to be what? Yeah. Yeah, it's going to do the 0 option right here. That now, when select is 0, this data that's on the 0 input, this 1, 1, 1, 0, it's going to be connected to the output. And look, the output goes to the AN bits, the analog or anode bits of the 7-segment display. And we talked earlier that it takes a 0 to light up a display, right? If you have a 1 for an anode bit, the display is not going to light at all. So do you see why this is 1, 1, 1, 0? Because what's 1, 1, 1, 0 going to do? It's going to what? Well, no. Remember that the anode bit just either lights up the display or shuts it off. To make a 0 on the 7-segment display, that's where these come into play. The seg output.
So it turns it off.
The rightmost one.
Yeah, how many displays are going to be off? 3. Yeah, the displays getting these ones are going to be off. Only this display is going to be on. And this bit here, that's the AN0 bit, okay, which is the furthest to the right bit. When you're looking at the basis board with the switches on the bottom, the 0 display is furthest to the right. So you see, this is only going to light up the furthest to the right 7-segment display. The other 3 7-segment displays are going to be turned off. Okay, so when is the carry out a 0? You said it a little while ago.
Yeah, we got number 0 through 15.
Yeah, when you don't have a carry out, your addition results 0 through 15. So you see, the result, you know, any addition result 0 to 15 will be displayed on the furthest to the right 7-segment display. Okay, so does everybody see what's happening when this is a 0? Any questions? Okay. Let's say we have an addition that gives us a carry out equal to 1. Now the select is a 1. So now what's going to happen at the mux? So what happens here? What's the output of the mux going to equal if the select is a 1? Right, it's going to equal the data that's on the 1 input, which is all 1s. Now all 1s go to the 7-segment displays, right? All the anodes to the 7-segment displays are all 1. And what do 1s do to the displays? It shuts them off. So any result greater than 15 is not going to be displayed. All the displays are going to be off. It doesn't matter what the segments are if the display's off, right? You're not going to see it. Okay, so you see that's what the mux is doing. Through choosing one of these two inputs by using the carry as the select bit, we're either going to show the result if it's less than 16, or we're not going to show the result if it's more than 16. Okay? Does that make sense?
So we're not using all 4 displays.
No, we're not. Yeah, we're just using one display. I mean, it's a really good question, and we're going to talk about it more in a few weeks because, see, the way these displays are physically connected, they would all show the same data. Like, if you put all zeros here, so all the displays light, and let's say the result is 4, all 4 displays is going to show a 4. Okay, because they're all connected the same way, they're all connected together. In order to get the displays to show different numbers, like if you wanted to show, 1, 3, 5, 7 on those 4 displays, you have to use what's called time multiplexing. And we're going to get to a point where we do use all the displays to show multi-digit numbers, but that's not for a few weeks. And when we get there, you'll see that we'll give you a module that does it, because time multiplexing is not a trivial subject. It's a more advanced topic. But Dr. Mealy designed a time multiplexing module that we use to use all the displays. And like I said, that's in a few weeks. Is it next week? It might be next week. It's either next week or the week after. Okay. Okay, so any questions about how this works? All right, the next thing is I just want to show you the test cases for the overall. So these test cases are for after you have a successful simulation for your mux and your decoder, and then you go to test the whole thing. And that's where, again, you got to make a structural model to connect those modules together. It's taking longer and longer to turn with the bulb is getting worn out. Okay, so lab 3, you want to do the same 10 test cases that we did for lab 2. So the same 10 test cases that you use to make sure your RCA works, you want to do those same 10 because we want to make sure the RCA is still working the way it was working before. Just because it worked by itself, a week ago, doesn't mean that once you put it in this circuit, it's going to work. So you want to make sure it still passes those 10 test cases that it passed in lab 2, right? So the same ones, like 0 + 0, 0 + 1, and so on. Okay. In addition, you want to make sure that your decoder shows all the hex characters. Okay, so it's the 10 test cases from lab 2, and then you have to add enough test cases to make sure it's showing 0, 1, 2, 3, 4, 5, 6, all the way to F. Okay. I mean, some people, what they do is, they'll do the 10 from the RCA, and then they'll just do 16, make sure that it shows 0 through F. Other people, there'll be some overlap because, some of the characters are gonna be shown. When you do the 10 test cases for the RCA, and then they just fill in the gaps, but make sure. It's okay to have duplicates. When you do the test of the design, you make your video, it's better to have duplicates than to miss something, because if you just miss one, like say you don't show that it shows a C, that's not 100% working. So, I would say it's better to be redundant than to miss. Well, it's definitely better to be redundant and cover everything than to miss something. Because again, if I miss something, it's not 100% working. Also, you want to make sure that this part of the MUX is working, right? That when you get a result more than 16, which one of the test cases, or at least one of the test cases for when you're testing out the RCA, will give you a result greater than 15. So you should see the display blank. Okay. All right. So any questions on the test cases? All right. Just one more thing, and then you can get started. And I'll post this, but I'll talk a little bit about it before I post it. And that's the constraints for the 7-segment display, because you haven't done that yet, right? This is the first time you've used the 7-segment display. I'm going to post this, but when you look at the constraints file, you're going to see that there's this whole section for the 7-segment display. It says segment display. And you have to, what we call map, whatever you called your segment bits to the segments that are on the basis board as part of a display. So you'll have like seg 0, right? Seg 1, seg 2. And what I did is, I made, and I would follow the same thing. I made seg A, seg 0, this is seg 1, 2, 3, 4, 5, 6, 7. And then you also have to do the anode output too. So you have like AN0. So AN0 is the first in the constraints file. That's the top one. And then it goes AN1, AN2, AN3. So when you're looking at your constraints file, it goes seg 0, seg 1, seg 2, seg 3, seg 4, seg 5, seg 6. Now there's also this, you'll see get ports DP. DP stands for decimal point. We're not using the decimal point, so you just leave that. But then after that goes AN0, AN1, AN2, AN3. So I'll post this over on the wall there if you want to take a picture of it. Okay, but then you got your switches, which you've done before, right? You're gonna have 8 switches, and then this is the new part, right? No LEDs for this. Okay, you don't use any LEDs for lab 3. Okay.
But what's the light up?
Well, when I say LEDs, I mean the LEDs on the board. Like these LEDs. You're using the LEDs in the 7-segment display. Yeah, not the individual LEDs.
Wait, is this what you meant by like all 4 of the same thing? Because there's only 7 like display.
Right. Yeah. Exactly. It's not like separate ones because they're physically all tied together. Yeah, and then this thing called time multiplexing. Like when we get to it, I'll talk a little bit about it, but we don't go into a lot of detail because, like I said, it's like you don't design a time multiplexer because it's not easy. I mean, Dr. Mealy, we're going to use his design.
Is it basically just like making it so fast over each?
Exactly. That's exactly what it is. Yeah, that our eyes don't detect.
Yeah.
Yeah, that's exactly what it is. Yep. But the hardware to make that happen is not like trivial. Like you'll get Dr. Mealy's module, and when you look at it, it's quite a bit of code. It's more than what's expected in a class like this. Okay, so anyway, you should be set now to work on the activity. Again, the activity is filling out this table, and then you can get going on lab 3. You have enough information now to finish lab 3.